So this is the lecture for basically the entire unit. What we're going to talk about here is what you need to know about velocity versus time graphs and equations and all the things that we are going to be using during this unit. So the first thing says a ball is rolling down a hill at time equals 0 seconds. It is not moving. And each second it goes 2 meters per second faster than it did the second before. For example, at 0 seconds, it was going 0 meters per second. So I'm going to go ahead and put a dot here at 0 meters per second. At 1 second, it will be going at 2 meters per second. Well, let's just say, okay, so this is 2 meters per second. And so at 1 second, that's how fast it'll be going. And at 2 seconds, it will be going 4 meters per second. So at 2, it's going to be going 4 meters per second. And I'm going to continue this on. And so each second, we are going 2 meters per second faster. So now it is speeding up. Well, how we describe how it's speeding up is going to be called acceleration. So it says the slope of a velocity versus time graph will be the rise over run of the graph. In this case, it is how much it goes up or how much the velocity changes. So how much the velocity changes, so the triangle means change, divided by how much it goes over or how much the time changes. So this triangle means change. If you describe how much your velocity changes in 1 second, what is that? Well, in this case, how much our velocity changes each second is your acceleration. So now we have a definition of acceleration. So both we know that acceleration is the slope on your velocity versus time graph, but we also know that this is how much you speed up or slow down each second. So in this case, for the one up here, we are speeding up by 2 meters per second, because that's how much it changes every second. So every second you're going 2 meters per second faster, which means that my acceleration is 2 meters per second each second. And we need to also talk about what all of these variables mean. So we have x, x naught, delta x, v, v naught, delta v, a, t, and delta t. So I'm going to go through each of these. So position is x, that's where you are, and you measure that in units of meters. The little zeros, you'll notice them here and here. The zeros mean at time 0, and it's read as x naught and v naught. So the little zero, you read it as naught. And what that means is it's just your starting position or where you were at time 0. Or in terms of v naught, that's your starting velocity or your velocity at time 0. Okay, so this then is your starting position, m, because it's also measured in meters. If I wanted to know how much my position changes, that is also m, because it's also measured in meters. But the other thing I want to mention that this is also called displacement. Or if you were asked how far something went, that would be the same thing. And now I want to think about, okay, wait, so then what's the difference between your starting position and just position? Well, position is going to be where it is at a certain moment in time. Well, your question then is like, well, what time? So I'm going to say position at some number of seconds. And that some number of seconds is going to be whatever this time is. So if I put in 2 seconds, for example, then this is going to be the position at that number of seconds. So if I put in 2 seconds, then it's the position at 2 seconds. If I put in 3 seconds, it's the position at 3 seconds. If I put in 2 hours, then it's where is it at 2 hours? All right. And then the same things are going to happen for velocity. So regular v is the velocity at a specific number of seconds. So this is going to be the velocity at time some number of seconds. And again, that number of seconds is going to be determined by what this t is. And oftentimes it'll say like, hey, how fast is it going at 4 seconds? And so you'll be able to just put in 4 seconds for time and then solve for v, because that'll be how fast it's going at 4 seconds. Then we have your, we got to talk about units. Okay, so units, velocity is measured in meters per second. Your starting velocity is also meters per second. If I'm going to describe how my velocity changes, that's also meters per second. And then we have acceleration. So acceleration is how much your velocity changes in a certain amount of time. So we already talked about that as the slope on a velocity versus time graph. But I also want to think about what those units are. So the units for my change in velocity, this is meters per second. And then I divide it by the units of time, which is just seconds. And so this is the same as if I do meters per second times 1/seconds. So you can divide something or you can multiply it by the reciprocal, which means like just flipping it upside down. So I have meters over seconds times 1/seconds. So what happens is when I multiply this, I get 1 times meters, which is just meters. And on the bottom, I have seconds times seconds, which is seconds squared. So these are the units that you are going to most likely see for acceleration. Instead of writing it like this, where it's meters per second over seconds, you're going to see it written as meters per second squared, because this is a lot easier. Now, it really means what is that change in velocity each 1 second. But these are equivalent units. It's the same thing. All right, and then we have time. Well, time we always measure in seconds. And how much the time changes, we would also measure in seconds. So I would keep this page handy because not only is it going to help you remember what all the different letters mean, but if you're trying to figure out what a number is, it also is helpful to look at the units. So for the next part, it says using the variables above and the y equals mx plus b format, create an equation for this line. So we're going to take a look at this graph first. And we're going to remember that the slope of this line we just talked about is the acceleration. And the letter that we're using for acceleration is A. And then we're going to remember about the y equals mx plus b format. So when you have y equals mx plus b, the y is going to be the variable on your y-axis. So in this case, on my y-axis is a velocity. That means that instead of y, I'm going to put velocity. Now you could either write it out as velocity, or you could just write v. And then on the right-hand side, m is the slope. So in this case, our slope is the acceleration, or a. And then instead of x, we need to put our x variable. And our x variable here is going to be the thing in front of the parentheses on the x-axis, and that will be time. And now, last but not least, we need plus our y-intercept. Well, our y-intercept is our starting velocity, so that goes right here. And so that's going to be starting velocity. And so that'll be our equation. So we have velocity is equal to acceleration times time plus our starting velocity. And the one thing to notice is that I do a weird t. And the weird t is because when you're doing these equations, you always basically, well, not always, but most of the time you have a t next to a plus sign. And so if I do a t, that's always a t. This is always a plus. But if I do that, which one is it? Is it a t or a plus? And so I will not do this. My t's will always have a tail, just like they do in a typewritten thing. And a plus sign will always look like a plus sign. And so I encourage you to make sure that you are also doing something so that it's easy for you to tell the difference between a t and a plus sign. So we have a car moving with a velocity of 2 meters per second at time equals 0 seconds. So remember that my starting velocity is my y-intercept, so I'm going to start right here. That does not mean I'm starting at a distance of 2 meters like it was with a position versus time graph. This is literally how fast you're going. And so I'm starting and I'm already moving at 0 seconds. And it says I'm going to speed up to 5 meters per second at 8 seconds. So at 8 seconds, it's going to be going 5 meters per second. And so I'm going to draw that line like that. And then it says calculate the acceleration of the car. Well, acceleration of the car is the slope. And so the slope on a velocity versus time graph is rise over run. And so when I'm finding my slope, I just need to make sure that I'm paying attention to how much it goes up, which is not 5. It's starting at a height of 2 on here. And so when I start with a velocity of 2 and I go to 5, that means I'm going to go up 5 minus 2, which is 3. And then my run is how much it goes over, which I'm starting at 0 and going to 8. So that's going to be 8 minus 0, which is just 8. And then I need to think about my units. So the units for the 3 were 3 meters per second. So it increased by 3 meters per second over 8 seconds. So it took 8 seconds to speed up 3 meters per second. All right, then it says using the y equals mx plus b format, create an equation for this line. So I'm going to take and remember what I did up here. And I can even just take this equation and I'm going to put in the numbers. But I'm not going to put in a number for my y variable or my x variable. I'm just going to leave it because the height of this graph changes. So I don't know what it is all the time. So I'm just going to leave it as v. And then my acceleration is what I just figured out. That's this 3 over 8 meters per second squared times time. Again, time is changing as you go on. So times time plus my starting velocity, because that's my y-intercept, which is 2. Specifically, this is going to be 2 meters per second. Then it says, using your equation, if you kept speeding up at this rate, how fast would you be going at 25 seconds? So I want to know the velocity at 25 seconds, so I don't know v. So I'm going to just leave that there. But I want to know how fast it's going to be at 25 seconds. So instead of time, I'm going to put 25 seconds. And everything else is going to stay the same. My slope is the same. And my y-intercept is the same. And then I just need to put in my math symbols. And I'm going to leave out the units for right now. So I'm going to have 3 over 8 times 25 plus 2. And so I get a velocity of 11.375 meters per second. So this is how you use the equation for the graph to go ahead and find a velocity at a time in the future that is not on the actual graph. Then it says, when we were doing the constant velocity unit, we used the velocity versus time graph to determine how far you went. What represented how far you went on a velocity versus time graph? Well, that was the area between the horizontal axis and the line on the graph. So let's do an example. So if you were traveling along at 5 meters per second for 10 seconds, how far did you go? Well, on here, I've got 5 meters per second. Here's my 5 for 10 seconds. So that means my graph would look like this. So we're going back in time to our constant velocity unit where our velocity did not change. And when we did it in the last unit, we just found this area. So the area of a rectangle is base times height, which is going to be equal to how far you go, or your displacement. And that displacement is going to be your base, which is 10 seconds, times your height, which is 5 meters per second, which means that when we multiply that together, we're going to get a distance of 50 meters. Then it says you're driving a car at 5 meters per second and you see a stop sign ahead of you. So you decide to stop at a uniform rate, the same acceleration, in 10 seconds. So this is similar to the last one, but now I'm starting at 5 meters per second, but at 10 seconds I'm stopped, which means that my velocity is 0. So my acceleration on this graph is going to be the slope on the velocity versus time graph. And the slope then is negative because it's going down. And I'm going down 5 because I'm starting at 5 and going to 0. And that'll be divided by how much I went over, which is 10 seconds. So I will get a slope of negative 1/2. Now be careful that you don't do 1. You cannot just count boxes. You actually have to pay attention on this graph to what the scale is. Now it says, what is the equation for the area of a triangle? Well, the area of a triangle is just equal to 1/2 times your base times your height. And some of you say, well, it's base times height divided by 2. I don't care which way you write it, as long as you know what it is. And either of those are fine. This is how far did you go while you were stopping? Well, just like we found the area to find how far we went before, we're going to use the area to find how far we went now. Well, the area of this triangle is 1/2 base times height, and that displacement, your change in position, that's not a triangle X, that's how far it went, or your displacement, is equal to 1/2 times the base, which is 10, times your height, which is 5, and so that is 25 meters. Why is this distance different than the previous question? Well, if you think about it in real life, if you have two cars and one of them is driving along at a constant speed the whole time, and the car driving next to him that was originally going the same speed, all of a sudden decides it's going to slow down and stop. The one that keeps driving at a constant speed is going to go a lot farther than the one that's stopping. So you have to make sure that you're paying attention to these triangles versus rectangles, that you're paying attention to when it's going at a constant speed versus when it's speeding up or slowing down, because you will get very different answers. And specifically, if I want to comment on the graph, I can say the area of a rectangle is twice as big as the area of a triangle. But maybe we don't start or stop at 0. So what are we going to do here? It says now you want to create a general equation that describes how far an object went. But now I've got all this crazy stuff happening. So if we want to write the equation for the area of a rectangle, the area of a rectangle is just base times height. And the area for a triangle is 1/2 base times height. But we want to write this in a little bit of a different way. So if I want to actually write this as the area of this particular triangle, I'm going to make this a little bit different. Well, I'm going to notice that for the rectangle, the width of my triangle is how much the time has changed. And the height of the triangle is my starting velocity, because it's always going to start at 0. So the height of my rectangle is V0. So for the area of my rectangle, I can say, well, that's the same as my base, which is my change in time, times the height, which is V0. And then I could say, well, let's now think about the triangle then. This is 1/2 times my base, which again is the same base. That's my change in time. Now the height of this triangle isn't just V, it's because it's going from V0 to V. So if I want to find out how tall this is, I'm going to have to think about it as the difference between these two. So this height then is going to be V minus V0. Well, that is also written as your change in velocity. So I can look at it as how much my velocity has increased over some amount of time. So I'm going to say, okay, so that'll be times my change in velocity. Now this next part is a little bit weird, so bear with me here. I am going to remind you that acceleration is equal to your change in velocity divided by your change in time. So it's how much your velocity changes each second, or it's how much your velocity changes in a certain number of seconds. And I've got this change in velocity thing So instead of writing that, I'm going to say, well, I kind of rewrite this. I'm going to multiply this acceleration is equal to your change in velocity over change in time. I'm going to multiply both sides by change in time. And if I do that, then I have this is going to be the same thing as my change in velocity because the change in time will cancel out. And then all I need to do is I'm going to put this back into this red equation. And I know this is weird and you don't have to memorize how to do this, but if you do it once, it's good enough. All right, so we have 1/2 times your change in time times, and then I'm going to put this thing in for change in velocity. I'm going to stick this in there instead. So I'll have change in time times acceleration. Well, if you have x times x, that's equal to x squared. And this change in time thing, well, that's silly because I'm starting at 0 and going to time t. So I'm going to just call it t. So I'm going to say that this is the same as 1/2 times t times a. Well, t times t is t squared, so I'm going to go 1/2 times t squared times a. But that looks gross having the t squared in the middle, so I'm going to say that that is the same as 1/2 times acceleration times time squared. Okay, so if I do that, and I want to figure out my total distance that I traveled, I'm going to need to include both the triangle plus the rectangle. All right, well, your triangle is this part that I just did, so that's this. And I'm going to add to it the rectangle part. And so here's the rectangle part. And again, I'm going to say, hey, you know, that change in time thing, I'm going to just say, we're going to say we started at time 0. So this would be time times, but I don't want time in the front. I like velocity in the front. So I'm going to go v naught times t. All right, so we're going to take this part then, and we're going to add that together. Well, all right, so we have then how far it went, or the area, is equal to how far it went, which is your change in position or displacement, is equal to this 1/2 at squared plus the rectangle, the area of the rectangle, because you are going at a certain speed. So this displacement thing, this is really just x minus x naught. So where you ended versus where you started, which is kind of gross actually. And so what I want to do instead is just add the x naught to both sides. And when I do that, I'm going to end up with the general equation for this unit. And you will not need to memorize this equation, but you do need to be able to use it. And so this is the aha ta-da moment of how you use the triangle and rectangle and the area on a velocity versus time graph to tell you how far you went. And then it's up to you to create your own definition for what velocity it is and your own definition for what acceleration is. Good luck, and let me know if you have questions.